Hello everyone, this is my organic chemistry spiel on the differences between E1 and E2 reactions. I hope you enjoy. So we're starting off by understanding what happens when we mix
our tertiary bromine with our hydroxyl group.
This is going to be an E1 mechanism because of the tertiary complex that you have. You have these three carbons that surround this bromine. So there is a fourth point. So the bromine is going to want to come off rather than it being taken off from the strong base. So to find out how to do this,
I created the art version of the chemistry. So what we have here is we have exact models of what these molecules look like.
Each carbon represents a tangerine, and each of those has single bonds, just like before. Where this part of it represents the molecule that is facing outward, so it's pointing towards you, if you can imagine that. And the back one, where it has these lines that are staircase-like, means the molecule is pointing behind you. So you can imagine the center carbon as a paper in front of you, and there's one carbon in front and one carbon in back. The bromine is recognized by the little artichoke that we have here. This OH group is a tangerine in blue that is connected to our hydrogen strawberry. And here's how the reactions will take place on paper.
What happens is this bromine is going to take off because with E1, this bromine wants to take off. You have this carbocation, which is a positive charge that occurs at this bromine spot. So the bromine comes off and it comes off as Br and it takes the bond with it, so it's a negative charge. The positive charge, to balance out the charges, stays on this tertiary carbon. That tertiary carbon turns to a hydrogen, and the hydrogen wants to take that positive charge away. Now that we have the carbocation, the minus on the OH is going to attach to the plus. So what we have is now we can take the OH, and this OH will attach to this plus. The purpose of this elimination reaction is just to eliminate the bromine. So once we have this, and when we add the hydroxide, the general case is that a hydrogen that is attached as the fourth part of this carbon, with all carbons needing 4 bonds, there will be a hydrogen that then folds onto that positive charge, creating a double bond. So your final product will be something that looks like this, where you have a double bond placed at one of these carbons. It could be any of these carbons, and you have single bonds on the rest of the carbons. The main point behind this reaction is that we are eliminating this bromine.
So the product of this reaction is going to look like this on paper, just like before. And here is the physical representation where you have this double bond right here, and you have single bonds between the other two tangerines, or known as carbons. Next, we're focusing on what is known as the E2 reaction, where we have a bromine in the same situation, but instead of being attached to 3 different tangerines like before, it's just attached to one. This is an E2 reaction because we are focusing on the fact that this is a primary carbocation when this bromine is taken off, just like before. We also have our OH group with our blue oxygen attached to our hydrogen, and we are going to see what the mechanism is when you combine these two.
So the whole purpose of this reaction is just to eliminate, once again, this bromine. So what happens is the bromine leaves just as before. This molecule then becomes positive on one end, and the hydrogen folds towards the direction of the positive to neutralize the charge.
The products of this reaction
Would have been this ethene that has been created,
and bromine in solution.
when the bromine leaves, this is going to leave with a positive charge. This positive charge attracts the negative charge of this OH group, causing this to be a form of H2O. Now this is a very good leaving group, so this will gladly leave and it will fold back on itself. That's why we get this double bond ethene. And then bromine, which just left, still stays in solution.
To our physical representation, we have this primary bromine compound that
We have here, and we combined it with our strong base, and we created this ethene. So our carbon with 2 bonds attached to it.
Now we are going to move on to a special case where instead of 3 or 1 carbons, you have 2 carbons where it can fold either direction. Here we have our lovely model of a bromine. You may see there are 2 tangerines that are attached to the central or alpha carbon. So what happens when we combine it with our strong base hydroxide again? We'll figure it out.
Now, given the last two examples, we found that just like before, the bromine is going to leave this compound, which creates that carbocation we were talking about. So it's going to create a plus. And then we have our bromine minus, so the charges are equal. Well, now we have a choice. Are we going to have that hydrogen fold on the right side of the molecule or on the left side? And it turns out that both are correct. You can have that fold on the right side, and you can have that fold on the left side. These are enantiomers because they are the exact same compound. If you took this one and you flipped it and you have this mirror image right here, you will get this exact same structure.
So given that enantiomer, when we have this secondary bromine and we combine it with our strong base here, with our hydroxide, we get a enantiomer. I only had enough oranges to create one of them, but if you wanted to, this is the exact same compound as if you decided to flip it on its mirror image. All that would mean for the compound is that you take the carbon and flip it over. Now you have the exact same compound that we had before, considering them enantiomers. Thank you all so much for watching. This has been a great time, and I hope you enjoy my combination of the arts and sciences. Take care.